Our next speaker is Juan Spedaletti from the Universidad Nacional de San Luis in CONICET, Argentina. He will be talking about convergence results of the first Steklov eigenvalue in optimal windows.
Okay, I want to say thanks to the organization. This is joint work with Julián Fernández Bonder, Universidad de Buenos Aires. We work with optimal constants here. An optimal constant is the optimal constant of Sobolev Poincare, and the other optimal constant is the constant of the truss. The following facts guarantees the existence of the constant S bar. This immersion is compact for these values of Q and P, exists as sequence in this space, a minimizer sequence for the constant S bar. In the definition of the constant S bar, it's possible to consider normalized functions, and the Sobolev norm is lower semicontinuous. So these facts guarantees the existence of this constant. In the same way, it's possible to give conditions for the existence of these constants. Well, the function in which the infimums are achieved are called extremals. And these extremals are the solutions of these problems. This problem and this. This is the Laplacian operator, and is defined in this way, and this is the work derivative. This is the, for the case P equals Q, is the Steklov problem, and this is the Dirichlet problem. Well, we study a variant of this problem, of the Steklov problem. For doing that, we consider gamma subset of boundary of omega, such that the closure is not all the boundary, and the variant is this, where the first eigenvalue of this problem can be characterized in this way. This space is defined in this way, and this closure is taken in Sobolev norm. Heuristically are the functions in the space W1P that vanish in gamma. Well, we use the concept of the optimal windows. And for doing that, it's good to see some results in Bonder del Peso Neves, work of the year 2011, given alpha between 0 and 1. The author shown that exists gamma subset of boundary of omega, such that occurs that the Hausdorff method of gamma is equal to alpha be a Hausdorff method of boundary of omega. In our work, we consider the following problem. Given alpha between 0 and 1, if we define the following constant, like the infimums of the eigenvalues on the sets in the boundary such that satisfy that. The question is, it is possible to keep this infimum in a set in the boundary? Well, before to answer if it's possible or not, a subset in the boundary that satisfies that, it's called optimal window. This is the concept of optimal window. And for the answer, we see this theorem in Bonder del Peso Neves for alpha between 0 and 1. The author shown the existence of optimal window in the first part of this theorem. And in the second part, gives a characterization for the eigenvalue. It is fulfill this equality instead this inequality with more smoothness of the boundary of the domain. For example, interior spread condition. With this condition, it's possible to put the equality here instead of inequality. Well, what is the goal in this work? We do it in principle periodic perturbations of the domain. And we study the asymptotic behavior of the eigenvalues on these perturbed domains. We note that we can generalize these results. In principle, the perturbations are periodic, but after it's can be more general, the perturbations. In the case for the periodic perturbations, the results that we obtain are the following. The case, subcritical case, I less than 1. In this case, the perturbations are small, and the amplitude is small in relation with the period. And this is reflected in the fact that the sequence of eigenvalues converges to 0. Supercritical case, I greater than 1. In this case, the perturbations are big, and the amplitude of the perturbations are big in relation with the period. In this case, the sequence of eigenvalues converges to the eigenvalue on the domain without perturb. It's like the logical case. And the most interesting case is the critical case, I equals 1. In this case, the amplitude and the period balance it, and occurs the homogenization phenomena. In this case, appears a wave function m in the limit problem. So this is the most interesting case. So these are the results for periodic perturbations. It's good to see this work because our work is inspired in this work in Bonder, Oribe Rossi, work of the year 2007. In this work, the authors studied the asymptotic behavior of this constant. This constant is a variant of the Sobolev-Trace constant. And the domains omega epsilon are obtained from periodic perturbations from the domain omega. Well, what are the characteristics of this work? As said, they study asymptotic behavior of the constants as epsilon. They not study a sharp optimization problem. In our case, will be a sharp optimization problem. And the perturbations always are periodic, always periodic. Okay. How are these periodic perturbations? We can give a local expression for these perturbations. Let U an open domain, we can describe the fixed domain omega in this way. And after we take a function as a fc1 class function, periodic, with the period in this cell, and we do the lifting for obtain the domains omega epsilon. So the perturbed domain, the local expression for the perturbed domain can be looking this way. Well, taking into account these periodic perturbations, the result that we obtain are the following. A subcritical case, if I less than 1, the sequence converges to 0, and we get the following estimate for the sequence of eigenvalues, where this constant depends of the functions f and phi. That's the functions that perturb the domain. A supercritical case, if I greater than 1, the sequence converges to the eigenvalue on the domain without perturb. And finally, the critical case, I equals 1. In this case, the sequence converges to this constant. This constant have this shape, where the measure mu star is defined in this way, and the function m have this shape. So you say the function is defined in terms of the functions that describe the perturbed domain. So this is the result for the periodic perturbations. But we observe that we can generalize these periodic perturbations. That really matters is the change of variable of the perturbations. This is that really matters. And the perturbations that we will consider are the perturbations T epsilon, diffeomorphism, that satisfy the following conditions. T epsilon equals to identity on each compact set, and the tangential Jacobians converges to some function m in this space, and the convergence is Weck star in this space. So these are the more general perturbations that we will consider. Well, with these perturbations, we get these results. For these perturbations, more general perturbations, the sequence of eigenvalues converges to this constant, where this constant is defined in this way, and the measure mu star is defined in terms of this function m. This function m appears by the more general perturbations that we consider. And moreover, if u epsilon is an eigenfunction, then the composite eigenfunction, the scalar eigenfunctions, converge, it's weakly precompact. And every accumulation point is an eigenfunction for this constant lambda star defined here. Well, what is the idea for the demonstration of this result? If omega 1 and omega 2 are domains, and T is a diffeomorphism. This diffeomorphism induces an operator, operator tau, defined in this way. This operator is a very good operator. It's linear, continuous, and invertible. And the most important is that this operator satisfies these estimates. These estimates are very important in the proof. We define these functions, q epsilon and q epsilon q, with these applications q epsilon tilde, with this composed. This operator tau epsilon is induced by the more general perturbations. It's necessary to introduce these spaces, x alpha epsilon. The functions here are normalized. The space x alpha epsilon tilde, and the space x alpha star. The measure mu star here is defined in terms of the function m. So why all these definitions? Because with all these definitions, we can express the eigenvalues in this way. So how we need study convergence of these eigenvalues, study convergence of these eigenvalues is equivalent to study convergence of minimums. So for study convergence of minimums, we need a minima convergence theorem. And for doing this, we need some concepts. For example, the concept of Moscow convergence, because the functionals are in variable spaces, and the Moscow convergence gives an idea of convergence of spaces. The concept of uniformly coercive functional, the concept of the Weck-Lower semi-continuous function, and the most important, we need the concept of gamma convergence. This is the Georgi concept. In this space, this is not the classical gamma definition of gamma convergence, because here the spaces are variable. But we can show an equivalence between this definition and the classical definition of gamma convergence. It's possible to show the equivalence. So now with this, we can enunciate the minima convergence theorem. With this hypothesis of Moscow convergence, lower semi-continuous, uniformly coercive, and gamma Moscow convergence, we get these results. The first part says that for AHG exists UG in the space XG, such that the infimum exists. The second part gives the convergence of the infimums. And finally, for every accumulation point of a minima sequence, for G is a minimum for the functional G. Okay. So with this theorem, we can apply this theorem to the functionals q epsilon, and this gives us the convergence of the eigenvalues. So this theorem gives us this convergence, and this proves the theorem. And other important consequence is the convergence of the optimal windows in some sense. And this sense is given by the following theorem. Let gamma epsilon the optimal windows on the perturbed domain. If we define these measures is precompact for the Weck topology of measures. And every accumulation point of this sequence have this shape, where this subset gamma star in the boundary of omega is an optimal window for this problem. This problem is similar to the variant of the Steklov problem. The only difference is that here appears the function m. So this is the homogenization result that we obtain. Thanks.